Right, hello everyone. My name's Tom Ford. I'm from Oxford. I used to live in Cambridge, and I'm talking about some stuff I read in the literature. So I'm guess from Darren's talk, I'm that person pretending to be a scholar after your money, the rogue. So today I was going to talk about procedural generation, a review of a recent academic literature. Before I do that, I'll just tell you a little bit about myself. So I have written some 7-day RLs, some of which you may or may not have seen. So they're up here. I wrote a commercial game called Dungeon Ascendants. I've been working on see if I can work out how to use the laser on this thing. I've been working on a website. You can find details at these web addresses. And this year I wrote what I've been told is like a skiing simulator, where you can move left, right, and down. So do check those out if you have some time. So when I was putting together this talk, I thought, okay, I'm going to look at some of the academic literature on procedural generation and try and give you a flavor of that. So where do you start? Well, I looked to see if anyone had done this already. And there are a couple of interesting papers. Procedural Game Content Generation, a survey from 2011. Procedural Generation of Dungeons from 2014. And I noticed there's some people may be familiar with PCGbook.com. These guys have put together now a printed book which has come out in fact, just last month. And I think really, if you read this book, you'd probably get a lot more out of it than listening to my talk. So I do recommend checking these links out. There's a lot of roguelike stuff in there. I think people like roguelikes as a way of testing out procedural generation because they're so simple, sort of engine-wise. So I thought, no, I'm not going to give you a survey. What I'm going to do instead is I'm just going to pick on a couple of papers I thought were interesting, which feed into something I'm very interested in, which is relating story and space. So I'm going to do a bit more of a deeper dive into sort of 1.5 papers and show you what they're talking about and how that perhaps relates to roguelike development that I'm doing and other people are. So we've got 2 papers to review today. The one I'm going to spend most time talking about is Adventures in Level Design by an academic from Holland, I think, called Jay Dormans. This is a conference paper that was given in California quite a long time ago. And I'm going to touch briefly on a second paper towards supporting stories with procedurally generated game worlds, again from the same year, I think from Georgia Tech. So these are the questions these papers, I think, try to address. How are the story of the game and its game world interlinked? How can the story and the world be generated? And is the generation process influenced by the interlinking of story and game world? So let's start with the first paper. And this paper introduced 2 sort of new concepts or pieces of vocabulary that I found actually really useful. So it breaks the game down into, well, 2 parts of the game into these concepts, which are 2 graphs. And when we say graphs here, we're talking about objects that consist of nodes linked by edges. So the first one describes, they call it a mission graph. It's like, what are the stages a player needs to logically go through in order to complete this level or beat this game? So it might be something like you enter, you fight a monster, you find a key, maybe from a monster, you open a lock, and you leave, you're done. So that's conceptually the stages you need to go through to beat your level or win your game. Then there's another graph, which is the space that you're interacting in. So I've got some examples here. It might be a set of rooms which are interconnected, or in a roguelike, you could look at it as each square is a node connected to the squares around it, and that's your sort of spatial graph. So what we're going to talk about today is how do we perhaps generate these graphs, one which sort of captures how you play the game, or the logical stages to progress in the game, and one that captures the space in which we play the game. So in this paper, he starts with the Forest Temple level from The Legend of Zelda Twilight Princess, which I haven't played, and works out what the mission graph is and the spatial graph. And so I'll zoom into these in just a sec, because I'm sure you can't see them. This basically says I enter, I find a monkey, I defeat a guardian, and I've got some choices, things I need to complete before I can cross a gap. And this picture here shows the spatial outline of the level and where those items, the things you need to do, are found. So let's just zoom in a little bit. Here, as I say, to start the level, you defeat a guardian, and then you have to find 4 monkeys to cross a gap. You've got one already. To find this monkey, you need to find a key, unlock a door, and find it. When you've got your 4 monkeys, you can cross a gap. After you've defeated this guardian, you can go and get some secrets, and there's a couple of different paths that you need to follow, and you will need to do all these 3. Don't need to necessarily do them in that order in order to cross the gap here. If you look how this is arranged in the game world, it's not completely dissimilar. You defeat the guardian, and then you can go and access some of these secrets. There's a secret we see there. And there's a couple of areas where you find monkeys. But notice that defeat guardian is directly connected to crossing the gap. So this is a kind of Metroidvania style thing, where you come to a gap, you realize you can't cross it, you understand what you've got to do. But in order to do that, you need to go and do all these things. So there's clearly a strong correlation between this graph of things you need to do, the mission, and the graph of where you need to do them, the space, but they're not identical. Okay. So we're first going to look at how you perhaps go about generating some of these graphs in your games. The technique that in the paper they describe, I'm going to try and describe to you, is based on something called generative grammars. So apparently these originate in linguistics. Now, I don't know very much about these, so I'm sure feel free to correct me if I get stuff wrong. But we have a series of rules and an alphabet. And the idea is by using these rules, you can build up any phrase in the language. So as a simple example, I've got a sentence could comprise of a noun phrase and a verb phrase. A noun phrase could consist of a determiner and a noun. A verb phrase consisting of a verb and a noun phrase. Note that the noun phrase crops up twice. So our sentence can comprise noun phrase, which is a determiner and a noun, the dog. And the verb phrase has a verb, a noun phrase. Noun phrase is a determiner and a noun, so the dog ate the bone. Can be generated by using this series of rules. Obviously, when we get down to this point, we can pick, perhaps in procedural generation, a particular noun that's suited to the circumstances or at random. So how can we use this to perhaps think about building procedurally some missions for the user to undertake? So I'm going to set up some rules here, and we're going to see how we can use these to procedurally generate some missions. And if you think about my 2 graphs, we're looking at the graph on the left at the moment. That's the mission graph. So here's some rules. I'm going to start with this block. And this block can be replaced by an entrance, a goal, and some sort of challenge in the middle. That's the structure at a really basic level. And what could a challenge be? Well, it could be a monster, or the challenge could be a hazard. Okay? And the idea is anything that's a square is going to get replaced. And I'll keep doing that until I've got something that only comprises of circles. So squares are non-terminals and circles are terminals. So let's look at an example. Okay, I start. This is the gross structure of my mission, entrance, goal, and a challenge. Here are my rules for what a challenge can become. So I might pick one at random. And here I've got a very simple mission for my game. I enter, I fight a monster, I finish. So let's look at something that's slightly more interesting, a slightly more complex mission graph. So here, the gross structure is I've got an entrance, I've got a boss monster, and I've got a goal. So that means I've got to fight my boss monster before I get to the goal. And I've got something in here which is going to get replaced. And there's a couple of options in this rule set. These 2 blocks here could just be 2 challenges in a row. Or these two blocks here could represent sort of perhaps an optional section where you've got one challenge one way and another challenge the other way. And a fork and a join here, as you can see. And I'm still keeping my rules that a challenge can be a mission or a hazard. So let's run this one through. So here's the growth structure of my mission. Entrance, something to replace, boss monster goal. I use a rule where I replace that with a branch. Okay. And then each of these C's in the branch I can replace with either a monster or a hazard, perhaps picked randomly or by heuristics. And then I end up with, as you can see, a mission to use in my game. And obviously if I'd picked something different here, if I'd picked the two C's in a row, the mission would turn out a little differently. And I think you can see by adding more rules, by increasing the complexity of rules, you can build up some really quite complex mission structures. Some points to make: you can have recursive rules, like this block here could be replaced by a fork and a join with blocks again. So you can see how if I ran that rule a number of times, I could get recursively set up missions. And obviously you'd want some sort of heuristical limit on that, otherwise it could potentially go on infinitely. A point he makes in the paper is you can define the feel of areas by using different rule sets, or different heuristics. Some areas might have more monsters, some areas might have lots of optional quests, some areas might just be very linear. And the designer can put some controls on the randomness by picking the rule set to use. And interestingly, you can apply some meta-generation effects as well. Let's say you want the second half of your quest to be harder than the first. Well, in your first rule, you could have a divide here or a meta instruction telling the game engine to make the game more difficult when that was crossed. So that's the graph on the left, how to generate that, or one way you could generate that. Now let's look to see if we could use the same technique to generate the space in which we play the game, and then we can see how we might combine them. So we're using generative grammars here to generate a space to play the game. So perhaps a little bit harder to understand, but let's assume that in our generative grammar now, we have a sort of a 2D spatial, I'm going to call this like an open node. This is something that can be replaced. Perhaps if I start with this one here, if you have an open node in a direction, you could replace that with this kind of structure, which has two open nodes here. So broadly what I'm saying is, let's call it an open node or an expansion point, could be replaced by a T-junction. An open node could be replaced by a bit of corridor, and then the open node again, so that can continue. Or, and indeed when we wanted to finish this, an open node could be replaced by a piece of wall. So how does that work in practice? Well, I could start my level like this with an open node. I could perhaps randomly or with heuristic apply one of the rules, in this case the make a corridor rule, and that would look like that. Then if I applied my T-junction to this node here, the level now looks like this. And again, let's say on the top node here, I apply the make a corridor rule. And then finally, to finish things off, I make all the open nodes into walls. And there you can see I've built a dungeon structure. And as I apply, again, with more rules and with some heuristics on how large you want the dungeon to be, you could make quite a complicated looking dungeon using generative grammars. Now, of course, there are a lot of other ways of making dungeons too, but you'll see where I'm going with this in just a sec. So we've now got a mission graph. Let's say we've built a mission for our player with generative grammar and a space graph. Well, the whole point of this is how we link the two together. And what they suggest in this paper is you start with your mission graph and you build a space graph from that. Okay? So I think that kind of feels to me natural when you're building a level. If you are sort of doing a level design manually, you'd probably think, okay, I want the user to start here, have a couple of fights, do a key lock puzzle, maybe have a choice, and then bring them together with a boss monster. So you sort of conceptually think about what you want the player to encounter, and then you would build a level to match that. And so that's what we're trying to get the procedural algorithm to do. So very simply, how might you do that? Well, let's go through this mission graph, and when we come across one of these monster nodes, let's make that a bit of corridor with a monster in it. When we come across a hazard node, well, let's make that a piece of corridor with a hazard in it. So to see how that's going to work, I have to resort to actually stealing the pictures from the original paper, because it gets a bit complicated. But what you can see here is this is a typical mission graph that's displayed in the paper. Without worrying too much about what the individual nodes mean, you can see there's a sort of split here. These Ks are keys you've got to get, and Km here is a multi-part key. You can see to get through to here, this lock at the end, I need to go and get all those Km nodes. So how would this work in reality? Well, here what we're going to do, we're going to go from a mission graph to build a spatial graph. So we start with this divide here in the mission graph. The way that's captured here is by applying the T-junction operator until you basically get enough open nodes to represent the branch. We then add this, which is an item behind a trial or something. So it's like a little challenge to do here and an object. And then here, this is a secret and part of this key we need. So before I go any further, how are these placed? Well, literally, this algorithm suggests you pick a random open node, which you'll see from the previous page, and you pop your, in this case, these double arrows mean these two nodes are placed together. You place those two mission nodes with spatial representation of them on one of the open nodes here. So you can see we're building up a map by taking the jobs the player needs to do and adding them to the map. There's a few interesting things here. You'll see that because of the way the algorithm works, picking a random expansion node to place down these blocks, whereas in the mission map, all we're saying here is these are things you need to do, basically, which could be you need to do both of them in order to get through to the end. It just turns out by random chance they've been put in a line in the spatial map. So this is an example where the spatial map can differ from a mission map, but the concept that you still want to do both of these in order to get to the end, which is captured in a mission map, doesn't change. Yeah, so let me just clarify that. There's two slightly different things that I've sort of confused here. So if basically the algorithm is that when you place a node, you place it at a random expansion point on a spatial node. But these double arrows represent things which are sort of semantically coupled or logically coupled. So imagine this this trial is a monster, and that's an item. Well, you want to be able to, want to enforce that a player fights the monster before he gets the item. And that's why the two are placed together. Otherwise, you get the monster here and the item here, which would lose the gameplay value. Okay? Talking about, so these two blocks, you can imagine, are just placed at the same time. The second point I made was, although these are separate on the mission graph, they are placed sequentially on the spatial graph, which is entirely possible and doesn't sort of detract from the value of this, that you have to do all of these things, but is an example of how the two graphs can differ. Okay, so in this example, we place a trial and a key, 9 and 10, and the lock that matches the key, and behind that is the final key, the sort of multiple key you need to open, which you can see here is captured by that triangle. So that key opens that door, you get a triangle, the other two triangles we placed earlier, and when you have all those triangles, you can open the final door to exit. So I hope that was reasonably clear, and that describes how we've gone from sort of conceptual understanding of what the player ought to do to a map which allows the player within an engine to go and do the mission that the designer, or in this case the computer AI designer, thought of. So I'm going to return to this in a little bit, but I think there's some interesting pros and cons in this approach. It's an interesting way of generating quite complicated missions with locks and keys, with monsters and rewards. You can create things like lock and key puzzles, and they're always solvable in this approach if you run it through. It supports interesting meta effects, adding difficulty spikes, etc., into the mission, which again you could put in logical places as a designer. However, it's got some fairly major cons, a simple algorithm I've described. The semi-random placement of rooms sort of breaks down any kind of long-range order. We're just scattering rooms all over the place. If we look back at the mission, imagine this went on a bit longer, you'd probably want things that occur later in the mission to occur further away from the start position, and you're not really necessarily getting that here. We could have something quite complicated happening which appears quite close to your start point. There's no control over backtracking, so even in this example we have to go sort of here and get that, and then go there and there and there, and then come back again. So there's no optimization around that. And something that regular players will notice, there's no loops in this graph either, in the spatial graph, which again adds to the backtracking, means it's quite difficult to actually play, and it cuts down on your tactical opportunities to fight monsters, etc. So it is just a simple algorithm in the paper. I think it's a really interesting one, but by itself, I don't think it makes a very satisfying game. You need to add quite a number of heuristics into the spatial graph growth in order to build something that's a bit more satisfying. And there are some ways around the looping problem, but it's dangerous just to start connecting stuff up, because you might break the mission, you might make something that's accessible, should be accessible only behind a door, accessible without going through the door by bypassing it. But you could start with, for example, a hub, and then build missions as spokes, which might give you some sort of structure, which is a bit more conducive to gameplay. So if you bear that in your mind, I'm going to touch very briefly on a second paper towards supporting stories with procedurally generated game worlds. What they did in this paper was assumed that they don't have to generate that mission. They've got a handmade mission or a computer-generated mission, and their colleagues produced this paper, which described perhaps one way of adapting and procedurally generating missions. And in their formalization, they had a story that consists of NPCs, places, things, and types, which is equivalent to this list here, which is equivalent to a mission graph we saw in a previous paper. So here's a mission. A paladin, which is you, takes a water bucket from a palace. The paladin kills a Baba Yaga with a water bucket in the graveyard. The Baba Yaga drops ruby slippers in the graveyard. The paladin takes ruby slippers in the graveyard and gives them to the king. You can see it's a list of what would effectively be nodes in our mission graph. These guys have done it as a list. So they're trying to conquer the same problem. They're saying, how do I take that mission and turn it into a game world where I can actually play? And they really make some very tough assumptions here. So they model it as, these ones in bold here are islands, so they're where these plot events actually happen. And the intermediate points in the graph are like filler. They're like, just walking through the forest trying to get from one place to another. And they make the assumption that, or they force these plot islands, to appear on basically just a linear chain, and in the order that they need to appear in the plot. So you have to go to the castle first, then to the graveyard, and then to the cave, but you may well be doing some backtracking as you actually finish the mission. They allow branching, but only in sort of this filler terrain. So what they then do, which is interesting, which is unlike in the previous paper, is they try and optimize this spatial graph for some certain parameters. So they say, okay, the designer and indeed the player can set their preferences. Do they want a longer game with more distance between plot centers? Do they want branches to explore? Let's indeed may try and make the terrain reasonable by saying, if you've got a piece of mountain, there's a 10% chance you'll find a cave in the next cell, and a 0.5% chance you'll find another mountain, etc. So you have a, without going into too much detail, you have this sort of graph of how likely terrain is to be sequential. And they take all these optimization parameters and throw it all into a genetic algorithm in order to evolve random spatial graphs, so things that look like this, that match their requirements and also match the requirements of a mission. Interestingly as well, they then take this as far as turning it into an actual game engine. So they say, okay, it's fine, I've got this map of these areas, but I need it to map onto a 2x2 grid like we'd have in a roguelike, such that I can actually render this in my game engine. So they use an algorithm called recursive backtracking to find a solution whereby the graph which they generated fits into a 2D array. If they can't, if there's no solution available, they then go back and create another random spatial graph for a mission. So here's some of their results. This is a sort of 2D map they've produced, which has these mission areas in it. And when they optimize, for example, for a larger world with more branches or a smaller world with fewer branches, they build up these different game worlds where the same mission can take place, which have some of these qualities they're looking for. So again, just looking at some of the pros and cons, what can I learn from this approach? Well, I think the idea of using optimization algorithms to create more optimal maps based on some parameters is a strong one we don't see enough of in roguelikes. It does deal with the problem of creating an abstract graph and then turning it into actual 2D terrain we can explore. And by the nature of their assumptions, they sort of, the game has quite a clear order in terms of here, 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 but that really only becomes because they have a very simple mission with no side quests. So again, there's no support for anything other than very simple missions here, and no consideration of backtracking or loops, etc. However, I think their approach, the optimization approach, is quite general, so I don't see any reason why you couldn't adopt more complex mission graphs into this, and to extend the optimization of the space you're creating to, for example, minimize backtracking, or put side quests as proximal to the main quest, etc. So, okay, I've talked about these two papers, and in the next couple of slides I'm just going to provide a quick summary and try and show how some of this applies to a game I've been working on. So, first paper, Dorman's, provides a useful vocabulary to discuss the field. I think the separation of the idea of this mission graph and the spatial graph is something that was new to me and really quite helpful. I think Hartsuk shows the value of optimization approaches to go from a mission to a game world. And remember, both papers try and go from the mission graph, what the play needs to do, into a game world in that direction. But I think both papers highlight that you need some sophisticated heuristics, not just random chance, in order to build at a level that's actually compelling for humans to play. So why am I so bothered about this? Well, back in 2014, I worked on a 7-day RL called Trauma RL, and its sort of interesting aspect is that, although you might not notice, it has quite a complex mission graph, which is semi-procedural, with multi-step missions, side quests. It has System Shock style logs, which are dropped in places that you'll need to go to in order to learn, well, basically, if you've got a mission, I'll drop clues that tell you about the mission in places that you have to go to in order to complete the mission, for example. And it's got key and lock style puzzles. So what I've been trying to think about over the last couple of months is, how do I take my 7-day RL, which had a relatively fixed mission that I'll show you, but generalize it so that I can generate mission procedurally and generate a game world in which you can beat that mission, or you can play that mission. And so I think the breakthrough for me was the idea of this mission map and this spatial map or spatial graph. So I'm going to try and apply the vocabulary of Dorman's to Trauma RL. just showing this is a picture of a game, or see a screenshot. It's comprised of a number of levels which have a semi-procedural, semi-randomized linkage between them. So there's some branching going on between the levels. So in terms of a spatial graph I have in my game, there's the level connectivity I showed you. You can go from medical to the lower atrium to storage, etc. Back again. So the levels are connected in a fairly non-obvious way. The rooms there's a graph of the rooms, which I primarily use for modeling the missions, and I can support loops and those kind of things. The way I avoid loops causing a problem is when I'm actually building the missions, I collapse all nodes in a loop into one node. And finally, you actually play the game in the very detailed graph, which is a game map, which is generated from the rooms. So just to tell you, this is how the mission graph in the game works, and this is sort of the thing I would like to start changing up and make more procedural in the next version. So if you play the game, you're in the first level, you have to destroy some cameras, and by destroying the cameras at a la System Shock level 1, you can open the first elevator. There's also an armory on each level, which has a key, which is normally, I think, on the same level. So as a side quest, you can go to the armory. Once the atrium's unlocked, there's a number of things you can do. You need to find a transponder, jam a transmitter, which unlocks an elevator to the arcology, but that's dangerous, so I guarantee there's an environmental suit which you can find before that. You don't actually have to take it to explore the arcology if you want to just run through it, but that's advised. In the arcology, there's a computer core key, which unlocks a computer core. You destroy some computer nodes, which basically unlocks a button in the bridge to enable a self-destruct. To get there, you need to find a bridge key, unlock it, enable a self-destruct, activate it at a reactor, and then escape in a shuttle. So a relatively complicated mission with some dependencies between the two. And how do I actually turn that into a game world? Well, what I do is I put in some constraints about where certain quests appear. So I don't actually fix the level they appear on, but typically I'll say, okay, well, clearly the cameras are on the first level to get out of the first elevator. The transponder environmental suits, well, they can be in a 2 or 3 levels you'll encounter early. The computer node's always in the computer core. The bridge key will be somewhere, but it's not in the arcology because there's other interesting stuff in there. So I put some constraints on the spatial graph from the mission graph, but not perhaps very many. But what do I do that's very different from what we saw in the papers? Like every other, as far as I can see, roguelike game in existence, I generate my spatial graph first. So I build a load of levels and I connect them together without really thinking much about the mission that people have to do. Why do I do that? Well, because I can use all the established roguelike level building techniques we have. The way the game works actually is by taking templates and sort of slotting them together and building up mazes like that. And those levels are then linked with elevators. But in order to get that to work with the mission, as I say, I have to slightly hard code some aspects of the spatial map, like which order the levels come in. So the bridge is last because it's most difficult, because it's at the end of a quest. But there's no sort of AI doing that. That's me hard coding in something into the spatial graph, which I would like to get from the mission graph to allow the mission graph to change and therefore to influence the spatial graph. The second thing I do is I generate a mission, which I basically make an implicit mission graph. I throw down NPCs, keys, logs, etc. Lock existing doors. I swap in rooms which I've generated as blank with quest rooms, etc. And in the modern versions of the engine, I can slap on extra quest rooms onto existing maps as required, but they typically appear at the edges. So how can I learn from the literature that I've tried to explain today into how I can make a better game with more procedural missions? Well, the first thing to do would to actually build this real mission graph. As I say, it's sort of generated by the game because it's slightly hard-coded and I sort of just build it imperatively. But I'd actually like to build that mission graph, perhaps using a generative grammar or something, and then once I've got that, I can start using it to actually influence the spatial arrangement of the world. So I don't think I can go right like the paper does and go from a mission graph and just create a spatial graph entirely from that, because I am locked into using roguelike level generation techniques. But I'd like to do things like substitute part of a main quest. For example, the medical elevator being locked by a key rather than cameras. And then, as I say, I replace the hard-coded constraints on the level connectivity with constraints derived from a mission graph, i.e. if there's something like the bridge needs to be later than the arcology in a particular mission, it might be different in another mission, and have that come from a mission graph rather than be hard-coded. And indeed, similarly, replace the semi-hard-coded constraints on the spatial positioning of quests, i.e. the things in red here, with constraints that come out of a mission graph. And I think by using Dorman's sort of conceptual technique of breaking these graphs apart, that is in fact achievable, whereas I've been struggling even to get a grip on it without reading these papers. So there you go. I apologize, it was been a bit of a rush through a couple of papers which are a little tricky to follow, but certainly I found reading and researching the literature has helped me think more clearly about my engine and take it into a direction I want to go. I think there are good techniques and ideas in the literature, but these are all little toy tech demos, effectively, the paper equivalents of those. There's certainly no ready-made engines, and I think a lot of the considerations that we have to deal with making fun games are not captured within the papers so far. So, I think that concludes my talk. Actually, just as an aside, this is an actual Trauma RL mission graph. I showed you the textual version. The game actually will build it for you, and so that's what it actually looks like. But I need to take that and use that intelligently to build my levels. Okay, that's the end of my talk. So thank you for bearing with me, and I'm happy to take any questions.
Hello, Tom. I'm curious about the constraints that you use on this. You said about the heuristics for the in particular for the level generator, making sure there's no. You said for gameplay reasons you want loops there.
Yeah.
I think for me also is a kind of an aesthetic design to levels, making sure it fits thematically with the content that you're producing, and also there is a certain way we want levels to look, and how you get that fitting in with the style of the levels generated. Because from the first part that you showed with the kind of gluing on these sort of trails and things, it looked like it would produce kind of octopus style levels where you start in one place and everything's like branching off from that. So how do you ensure, I mean, Trauma RL looks nice. What is it you're doing to ensure that the level generator is got the right constraints to work in that way?
Okay, so I'll try and answer that question in two ways. So I think there's a general assumption in the papers I discussed that you'll start from a mission graph and produce a spatial graph, produce a game world from that. That's probably entirely fine, and I said contentiously that if I was a real level designer, that's how I'd do it. I'd think of the tasks that the player has to do and then build a level around that. But I don't know if that's actually true. I think it's quite likely that, particularly if you're making a sort of, Quake 3 level or something, you'd probably build some interesting shapes and get an interesting theme behind it, and then perhaps think about choke points and that kind of thing, secondly. So it's interesting to challenge the original assumptions. I think the generative grammars for producing spatial maps it's probably relatively challenging. The actual answer to your question is by picking particular rule sets, you can influence how the graph would look. So the rule set I had was just T-junctions and corridors, but you can certainly add more interesting items to that. Building in loops is, I think, relatively tricky. But what the guy suggests in the paper is when those corridors come close together, you can join them up. But again, that actually causes a problem with his mission engine. So. Yeah, indeed. Or, I mean, you can also sort of ignore the whole 2D structure and go with a sort of Jeff Late approach of teleporting to another room every time you go through a door, which works. But I think for some of the aesthetic reasons you mentioned, and just some of the practical reasons that we have aesthetic level generators that work, I'm not going to go that far as a paper does and go from a mission to the spatial graph. I'm going to build the core of my levels with our traditional level generation tools which look nice. And then I'm going to sort of patch and hack the mission structure into those spatial maps. I think just from practicality, but it also makes things look nice and make them, yeah, playable. Well, I think it's taking a reasonable compromise between the academic conceptual way of doing it and a way that will actually work.
So, what's your opinion? Is building a mission map and then a special map better, or building a special map and then a mission graph?
So the way TraumaRL does it at the moment is that it builds a spatial map first, but it knows what a mission map is going to be secretly. I never actually build a mission map that you could look at. This is produced by the engine as a sort of afterthought. So the key is, when I'm hard coding, what I've hard coded into the game is enough of this to make the spatial map not break the mission. Okay, but that only works because I know exactly what mission's going to be each time within certain constraints. So if this becomes more random, I lose that information to guide the spatial map. So to answer your question, what I need to do effectively is to build this mission map, to take the most important parts of it, and then use those to guide the spatial map generation, but only to guide it, not to have such a clear link, as in the papers, between the mission graph and the spatial graph. Again, it's a bit nuanced, but the only reason my spatial graph generation in TraumaRL works and doesn't break the mission is because I already have in my head, at least in the code of the game, a bit of what the mission graph looks like.
When you have so for example, you build one level. Actually, with connection you have your mission graph blank, so you can fill it with your tricks and traps. Actually, isn't that better?
So I think in order to make a completable mission, you need to understand what the growth structure is. So if the last place you need to go to is a shuttle bay, that needs to have the hardest monsters. You sort of need to know that when you're building the shuttle bay and you're building the monsters. You don't want to get into a situation where you go from the easiest level to the hardest level in order to pick up a key you need to get to the medium level. And those are the kind of problems that you run into if you don't have a mission map in mind when you're building the connectivity of your levels. So I think you need to build a growth structure into the map, and then you can certainly add tricks and traps and little locked doors and armories, as a later operation on your already established map. And indeed, that's exactly what I do.
Okay, so the way I understood it in the paper is that they start with the spatial, they start with the mission graph first to avoid the problem where if you first create your map, you can have the problem where it is either too big or too small for the mission that is sort of procedurally generated, regardless of this map. So you can have a very simple map, and then you run your mission generator, and then it creates this huge story that you have to fit inside of it somehow. Are you worried about having this? Like, if you reverse this algorithm, do you think that you might have this problem?
Yeah, I mean, so again, the way the game works at the moment, I do the spatial map first, and I do the mission map later, and it is possible for me to run out of rooms, to run out of spare rooms.
But you have this at the moment, so the mission is sort of fixed-ish.
Fixed-ish, and I can still run into this problem. Because I don't control, because of the way the level generators work, it's random. I don't know how many necessarily spare rooms I can fit in. And it may turn out that the mission wants to place a room in a level that already has too many mission rooms in it. And that will just fail, in which case I throw it all away and start again. So yes, I can see that being a problem as I make the mission more random. However, I think you can use some heuristics as well. If your mission contains 15 nodes, then you need levels of about this size. If it contains 30 nodes, you probably need levels that are 2/3 extra big, for example. So
So you just would decide to cut off the mission at some point. Say, okay,
no, I wouldn't do that. I would just say that I will create the levels which, even just by a process of experience, I will set the level generators to be big enough to hold a mission. What you can do when you're building a mission, even using generative grammars, is to put a maximum size and a number of nodes in a mission, because you can say, okay, I'm going to stop building nodes that become really complicated once I've got more than 10 nodes in the map, 10 nodes in the graph. So the algorithm you use to build a mission can have a lot of intelligence in it to stop it getting too big. You have a lot of control. The way I described it, you don't. You just pick rules at random, but you can definitely say, when I'm at 10 nodes, I only pick terminal nodes from now on, which stops the mission map getting any bigger. So you can use quite a lot of intelligence.
right, thanks.
Someone else? Do we have some Twitch? Oh, yep, sorry.
On the graph that you've got there, you don't seem to have any. You have multiple arrows going into the certain things, which I presume means multiple dependencies.
Mm-hmm.
So what you don't have is multiple routes.
Define multiple routes.
So you need to get through a door.
Yep.
There's 2 different keys.
Yep. Okay, so yep, that. I don't think. Let's just try and remember the game. Actually, the way, although you don't see it in this graph, that does happen in the game. For example, this box that you can't see says medical security, which is a door which has 20 keys, those keys being cameras, and you only have to kill 15 of them. So that's a way, for example, a door can be set to open with fewer keys. So it's entirely possible to have 2 keys for one door, so you can pick up one or the other. That's covered in the mission here. That's covered in the engine, even if it doesn't appear in this mission. I think the reason that I turned those off was it was just, particularly the computer cores and the medical security were just huge numbers of nodes.
I guess just like normal sort of nomenclature for this sort of normal way of showing this would be the arrows meet before actually going into the dependency, whereas 2 arrows into a thing would normally mean 2 separate ways. Do you understand what I mean about?
Yeah, I do. I mean, this is me throwing the nodes at graph viz in a simple way. So it may be that I could come up with more complex nomenclature which could capture that nicely. It might be worth looking into.
It looks like that was the last question. Then, thank you.
Okay, thank you.
Presentation.